I'm a solution architect at Xantaro. Who the fuck is Xantaro was a question we've seen around all week. We are basically a service integrator, and we are taking building blocks from different vendors, from different software providers, and we building a whole solution from it. So we are no vendor, we have no hardware, we have no software, we have no controller. Our product is basically the service you can deliver on top of your network while we help you doing this. We are here with one of our major partners, Juniper, just bringing up here. Their solution will be integrated a little bit in the proof of concept I did, but it's mainly vendor agnostic, what I'm presenting here. I would like to talk a little bit about traffic diversion, so on and off ramping of traffic in classical networks. The purpose of doing it usually is when you're trying to implement some kind of scrubbing device for DDoS mitigation, you have to somehow off-ramp attack traffic to the scrubbing device and have to re-enter the traffic into your network without creating any kind of loops, any kind of routing anomalies. Usually you have a two-part solution. You have some detection device which then will inject routes via BGP into your existing core network, and then you will have to redirect traffic to a scrubbing device. This will most of the time lead to a situation like shown below. We inject traffic to go for a specific target, 6666, because we want it to be scrubbed. It's redirected to the scrubbing device. Traffic will be cleaned, will be sent back to the device in the core layer. Unfortunately, the core layer knows that every traffic which has to go to 666 has to go to the scrubbing device, and we have an eternal loop which we can never break. So classical approaches to deal with these kind of problems where let's build large and complex MPLS VPNs on top of it. There's a clean VRF approach, a dirty VRF approach. I don't want to bore you with the details, but believe it or not, there are customers outside there which have not implemented any MPLS at all, or would have a hard time to implement any of these layer 3 VPN solutions in their network. We would gladly help them to implement that, but sometimes you cannot implement MPLS on your existing network. Other classical approaches would be to build some kinds of IP tunneling on top of your existing network. So use GRE or IP and IP tunnels, whatever you would like. It increases the complexity. You suddenly have to be able to terminate IP tunnels on your customer aggregation routers. Your MTU will go down because suddenly you will have to take care for additional headers. So not a real solution for most of the customers. Also, most GRE implementations these days are still software-based. Sometimes they're accelerated by some kind of acceleration modules, but in classical networks, it's hard to implement GRE tunnels. So there might be a new approach we can do with using SDN technologies, with using OpenFlow. Short disclaimer, it's not my original idea. It was published on the internet way before I thought about it in an article series on packetpushes.net. It's not 100% what was presented there, but I took some parts of that and put it into our integration solution. Just gave the references here, so not my original idea. The idea behind that is, I've called it SDN Magic down there in the corner. The idea is we still have the normal architecture I described before. We have a border, a core, and a customer aggregation network, and we need to get the traffic off-ramp to the mitigation device, and afterwards we need to forward it back through the network. What I do is, I will go into details when I'm zooming in into the specific parts. I'll take the red traffic, which is the attack traffic, send it to the mitigation device on the below. Afterwards, clean traffic, which is green, will come back to my OpenFlow switch. Some SDN magic happens, and I will turn it into blue traffic. Blue traffic, which can be delivered through the network just as classic IP traffic without any additional needs. You just need to know where to forward the blue traffic. There is information which is coming via SDN Magic from one of the routers in the middle. Blue traffic will be transported to the other end of the network, and there the reverse magic will happen in order to just translate it back to the green traffic we need to forward it to the client. So we have broken the looping in the network. Let's move in and zoom into specific parts of the solution and see what happens. We have two OpenFlow switches, one on the left side of the network, one on the right side of the network, and what we only do is we provision a couple of flows which perform specific actions. On the on-ramping, so where the traffic is going to the mitigation device, we just basically program two flows. The first one is very easy. Everything which comes in on port 1 has to go out on port 2. We can add an additional match condition just to make sure that the right traffic is forwarded by our application, so that it's only for a specific destination IP, the IP which was under attack before. After it was cleaned and the green traffic will come back up from the mitigation device, there's a more complex flow going on. We match on everything which comes from this port, even from the destination IP we want to go to, and now the magic happens. We change the destination IP address to a temporary IP address, the blue IP address we have in our network. We might need to change the destination MAC address as well, because up until now, no real routing has been taken place. So the destination IP address is still the destination MAC, the destination MAC address is still the MAC address that the original router once put into the packet. And most routing implementations today are very allergic to getting their own MAC addresses back or getting traffic to MAC addresses which are not located on their interface. And last but not least, send it out back on port 1 so it gets back to the network, and it's blue traffic. It can be forwarded through the network without any problems, just normal plain IP traffic. It may write on top of IP MPLS, it may write on top in layer 3 VPNs, but you don't have to deploy it in order to get it to the other end of the network. When we're reaching the customer part of the network, we have to retranslate it back to green traffic. Action is pretty simple. Everything which comes in on port 1 matches the temporary destination IP, so destination IP2 will be changed back to the original IP address, and maybe you have to change back the MAC address because the reasons I told you before still apply there. Router may not like it, and push it back up. So it's basically a distributed, if you want so, stateless NUT approach, because there are no network address translation states, so there's no state for every single client which needs to be translated, but only for every destination IP which needs to be translated. The other part of the magic is how to tell the network that it needs to route certain information a different way. It's still like in the classical approach. Somebody will send information that you'll need to send every traffic to the attacked IP address, which is still 6666, to the scrubbing device. I'm talking about the router in the middle, which sends 2 BGP announcements, one for send every traffic down to the scrubbing device, and there is another information which I call the blue next hop or blue traffic. If you ever encounter blue traffic in your network, you'll need to send it to the blue next hop. The customer aggregation device, in turn, will just make sure that the blue next hop is available in the network. Until here, it's just normal plain IP routing. No SDN Magic has happened anywhere, so you can deploy it in basically every network around there which is out there. No need to do anything. There are just 2 things specific there. We need 2 static routes, one pointing down to the scrubber next hop, one pointing down to the blue next hop. There might be specialities on some routing platforms because the next hop will probably not be resolvable because there's no router which represents the next hop. If you have a routing platform which is capable of doing static routes to a specific interface, fine. Sometimes you will need to do specific workarounds like binding static MAC addresses to the route, but it's as simple as to configure 2 static routes and have a central device which is part of the SDN Magic solutions we saw earlier, which will inject the traffic. Let's get a bit more into where most of the magic happens. We have a user which wants to redirect traffic through our new platform. There is a CLI script. It's just a sample implementation script I wrote. I'm using bash scripts because that's the way I work. But it basically, you need to provide the IP address you want to redirect, a temporary IP address which can be used in order to make it blue traffic in the network, and what you want to do. Do you want to wash it, so send it to the mitigation device, or do you want to remove the state from the network? What I'm using in my proof of concept is I'm using OpenDaylight, which is basically the mediation device between my script. So it provides a RESTful API, which will never change, or at least during versions, but should be stable enough. And northbound, in this case, it talks OpenFlow to the switches, so I can just use any switch which is capable of doing the needed actions, can be programmed with the needed OpenFlow switches, actions. The second part of the solution is basically any routing daemon you can somehow configure or automate. For this proof of concept, I chose BERT. I did implementations with XRBGP. You can even try to use the embedded BGP code from OpenDaylight and build your application on top of there. It's something which just has to be announced to BGP routes. It doesn't have to speak BGP, it doesn't have to pass any received routes, so no need for large-scale routing. I just chose BERT because I've never used it in a project before and I thought it would be nice to see it there. The solution comes down to a little bit of config file creation for creating these static routes, just a daemon restart or resynchronization, and your network is up to speed. It knows where to route the traffic, it knows what to do on the switches, and all you need to do is provide one line of CLI usage. I wrote a CLI interface. You can even imagine doing it with a web interface or any interface you want to give your operations people. You can integrate it in your processes. You can try to integrate it into your automation, automatic alarm triggers. These solutions does not provide any detection of DDoS. It does not provide any mitigation. It provides the opportunity to integrate mitigation devices in existing networks. Last but not least, I would like to give you a small packet walkthrough, because most of what I told you is probably pretty abstract, especially after going into the details. But it's pretty easy when we're breaking it down. It's a 10-step process, so I just wrote the destination IP address on every of the segments to make it clear which destination's IP addresses are used. It comes in with destination IP address 666, will be forwarded to the scrubbing device, because we injected a route to let the network know that red traffic or traffic to 666 has to be sent to the mitigation device. The mitigation device does its job, it cleans the traffic. The clean traffic comes back to the network. It hits our OpenFlow switch, which does the first step of the magic. It translates it into blue traffic. I've chosen 10.10.10. It can be private IP addresses, something you are not using in your network. Maybe public IP addresses, something you're flying around. Having IP addresses lying around is not usually a thing. You could even think about using it for IPv6. You could even try to reuse IP addresses at different points of your network. Doesn't matter in this example, just for clarification. We make sure the network knows how to send blue traffic to the OpenFlow switch on the right, and the reverse magic happens. Packets with destination IP 10.10.10 are sent there, and the original IP address is translated back, so traffic will go back to the original destination. Everything is fine with no loops, and we have a good and scalable solution. If you need to wash additional targets, it's pretty easy. State will not dramatically increase on the OpenFlow switches. It's just one additional flow per IP address you need to wash. It's no network address translation state like you originally know on your network address translation platform, so no source-based state, only a destination-based state. A fully virtual prototype was built. I was using the building blocks I described before. For the router platform, I just used Juniper Virtual SRX. I built a small SDN appliance, as I just called it, where it's basically a Linux VM running the Open Daylight and the Bird routing daemon. The OpenFlow switches I replaced with 2 Linux VMs just running Open vSwitch, because Open vSwitch supported every action I needed. Just a quick, show of what it's capable. It's completely portable, so every development can be done on a laptop, on any top of any virtualization environment. In this specific example, I have not included any mitigation device, so we can see the small OVS patch cables on the top and the bottom switch, which are basically replacing the mitigation device. They will not do any cleaning, but they will just forward the traffic back so that we have some integration point there. Stuff we saw, so some challenges and some stuff we still need to do. The change destination IP action is not widely implemented in OpenFlow switches, routers, and technologies out there right now. So we still need to find a cheap may vary, but a reasonably good priced OpenFlow capable switch which supports all the actions. A second train might be that we investigate further into how x86 hardware is capable of performing when just passing these simple flows. For example, we never benchmarked a normal off-the-shelf server how many packets it can do. It's on our agenda to stress it a little bit with our router testing platform, generate 10, 20, 30 gig of traffic and see when a normal unaccelerated server will break down. I've had to talk to a couple of vendors around the fair. Some of them see that there are opportunities for the future. Not all of them have capable solutions. We have acceleration technologies for x86 as well. We'll see where this may lead us. Right now, I showed you a solution where we have 2 OpenFlow switches in our network. We might look into integrating these as virtual switches into our routers and our routing backbone. Vendors like Juniper, Alcatel, Cisco are currently capable of doing virtual switching with OpenFlow support in their larger, higher-end routers, but they are lacking some of the actions. So once again, it comes down to it needs to support all of the actions. The OpenFlow vSwitch on Linux supports all actions, but we don't know how performant it will be if we get down to see how it works on x86 hardware. Yeah, just a quick summary. It's basically integrating a service. We're taking existing building blocks which are out there. We're taking the Open vSwitch, Open Daylight, routing daemons. We are taking existing vendors, not only open solutions, but also existing solutions, applying some glue, scripting, APIs, all of the stuff you see, and we provide a new service on top of it, and that's mainly what we do. It's coming back to my initial statement. Our product is basically the service, so we don't sell a controller we build, we don't sell hardware we build, but we will make sure that everything fits into your network and that it works fine in the end. One last statement, especially through the last years, you could imagine that you'll have to replace everything in your network if you want to run SDN and OpenFlow, and it scared away a lot of our customers as well, especially larger service provider customers are not ready to replace their complete network. So you don't have to get out your sledgehammer and get rid of all of your existing network. You can just integrate it wherever you need to use it for specific problems. Let's say the 5 or 10% of problems in a normal network you couldn't solve with existing protocols and stuff you already had on hand. So it's not a sledgehammer, it's more like a scalpel to get into smaller corners, use it where you need it, and solve your problems. So once again, I'm finished too early, 5 minutes for questions, but on the other side, it's better to get to lunch early, so if there are no questions.
Well, let's see if there are any questions from the group for you. I know I had just one from a technical point of view. Did you just take your own Open Daylight distribution, or did you have it come from? Was it just a regular community distribution?
Yeah, just a community release of Open Daylight. Just took it out of the repository. Used whichever was recent when I did the first implementation. The only thing I needed to change is back when I did the proof of concept, OpenFlow 1.0 was still the default. I just changed that bit to make it use OpenFlow 1.3, and that's all which was needed to make it fit.
Right, understood.
Okay.
Great, thank you very much.
Thank you very much.